Good afternoon, students. Are you able to hear me?
Yes, sir.
Yes, sir.
Get started. So yesterday we started electromagnetic induction, right? Chapter 6. We'll continue with that. So in yesterday's class, we discussed about the Faraday's law of electromagnetic induction, right? Then we started with the basics of Lenz's law. So is there any doubts from yesterday's class that you guys have?
No, sir.
Okay. Just give me a second. See, yesterday we did some problems based on Faraday's law, right? So what does the law state? It states that change in magnetic flux with respect to time does what? Induces EMF. Right, that is what this law states. Right, and we saw that EMF is equal to minus d phi divided by dt, or EMF is equal to minus delta phi divided by delta t, where this is the average value and this will give you the instantaneous change of flux with respect to time. So we did some problem based on this concept, right? Now what we will do is, I'll just give you one more example. Suppose the question is like this: phi is equal to phi t square plus 3t plus 2. Okay, and you are asked to calculate the EMF at 2 seconds. Okay, magnitude of EMF at 2 seconds. And in the second case, you need to calculate the value of EMF that is getting generated, or I will say the magnitude of EMF that is getting generated between 2 seconds and 3 seconds. How to do this? Now, if you observe this question, flux is what? It is a function of time. So flux depends on time. And when you're asked to calculate the EMF at 2 seconds, at stands for instantaneous value. Wherever you see the word between, it stands for average value. So that is a hint, right? So when you are asked to solve the instantaneous one, you are going to take this formula. So E is equal to, here I'll take only the magnitude, okay? Magnitude, here also magnitude. So EMF, can I write it as d phi by dt. So what is d phi by dt? It is going to be 10t plus 3. So what is going to be the value of EMF at 2 seconds? There's going to be 20 plus 3, that is 23. Right? It is going to be 23 units. Similarly, what is going to be the value of EMF between 2 seconds and 3 seconds? So E is equal to delta phi divided by delta t. Right? So if I want delta phi, I will calculate the final value minus initial value divided by the final time minus initial time. So what is the final value? So final value will happen at 3 seconds. So it is 5 into 3 square plus 3 into 3 plus 2 is the final value minus 5 into, what is the initial value? It will happen at 2 seconds. So it is 5 into 2 square plus 3 into 2 plus 2, the whole divided by 1. Right? So what is going to be the value? It will be 5 into 9 plus 9 plus 2 minus of 5 into 4 plus 6 plus 2, the whole divided by 1. So 45 plus 9, 58 plus 2, 60 minus 20 plus 8, 28, the whole divided by 1. So 40 minus 28 is going to give us 32. So these many units is the answer. So I hope you guys are able to understand. Okay, see, these kind of problems are not there in textbook, but if at all they put a question like this, you need to know how to find the instantaneous and the average value. Right? Please note it down. Right? Done?
Done, sir.
Good. Come. So let's go to the next concept. So I started with Lenz's law, right? So yesterday's class, we saw, I gave you an outline of what is Lenz's law, right? See, suppose there is a coil like this, okay, where you see the coil from this side, okay, and let's say you have a magnet in your hand, North Pole, South Pole. Now, if you drop this magnet, what will happen is the North Pole will be approaching towards the coil, right? So when the North Pole is approaching towards the coil, what will happen? So when the North Pole is approaching towards the coil, flux is going to increase, right? So magnetic flux will increase. When magnetic flux is increasing, what will happen is, see, when I say increase or decrease, there is a change of flux, right? When it is going to happen, then can I say EMF is induced? So this is a chain reaction, right? So flux increases, due to which EMF is induced. So when EMF is induced, I can say current is going to get induced. So when current is going to get induced, the direction is what is important. What is going to be the direction? Okay, right? So the direction of current is going to be what we are going to see in this context. Now, listen to this carefully. When any pole, I'm taking, see here I'm taking the example of North Pole. Instead of North Pole, if I had a South Pole, okay. So whichever pole, if it is moving towards a pickup coil, I told you what is a pickup coil, right? So pickup coil is the one in which the magnetic field will get induced. So if the magnet is moving towards a pickup coil in a way where there is an increase in flux taking place, then the current will get induced in such a direction that the same polarity will get induced. So when I say same polarity as that of magnet approaching the pickup coil. Okay. So this is what is going to happen. You're able to understand? Same polarity as that of magnet approaching the pickup coil will get generated, in the sense when the North Pole is moving closer to the pickup coil, then the current will get induced in the anti-clockwise direction when you see from the top. As a result of which, what pole will get generated?
North.
Yes. So when you see from the top, it will be a North Pole. Okay, I want you all to make a note of this point. Same polarity as that of magnet approaching the pickup coil will get generated. Okay. Second. So if there is a decrease in flux, then the EMF will get induced in such a way that the induced current will produce the opposite polarity of the magnet. Okay, means if the North Pole is moving away, for example, if I take the same case in consideration, if the North Pole is moving away from this coil, and when you see it from the top, then what will happen is there will be a south pole that is going to get generated. Means the current will be in the clockwise direction. The current flows like this, so that when you see from the top, it will act like a south pole. So you're able to understand this point? Right.
Yes.
And this law is what is, and this is because of the law called as Lenz law. Okay, let's see the statement for it. See. So the statement for Lenz law is this thing. Please make a note of it. The write it down, okay? The polarity of induced EMF, the polarity of induced EMF is such that it tends to produce I repeat, the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. Which opposes the change in magnetic flux that produces it. Means it will always oppose the cause. Okay. And secondly, you need to make a note that Lenz law is based on the conservation of energy concept. Okay. Listen. So this is the example which I told. When North Pole is approaching towards the coil, and when you see from the side of the magnet, then you will be seeing that the current in the loop is flowing in the anti-clockwise direction, and you have a North Pole getting generated. Similarly, if the North Pole is moving away, then the South Pole will get generated. That is why the opposite effect. And one of the reasons why there is a minus sign for Faraday's law, and it is because of the significance of this law. Okay, and this is a very, very, very important law because the whole chapter runs on this concept only. So this whole, if you have to understand this whole chapter, there are only two important points you need to register in your mind. One is EMF can be generated only if there is a change of magnetic flux with respect to time. That is first point. And the second important point is if the second important point is the direction of induced EMF according to the Lenz law. So these are the two important points to be kept in your mind. Clear? So we will be doing some problems which are based on this
Could you
concept.
repeat the second one?
I'm saying the second one is you need to understand the direction of induced EMF on the basis of Lenz law. Okay. Now listen to this carefully. So if you take this example 6.4, so in this figure 6.7, it shows planar loops of different shapes moving out of or into a region of magnetic field which is directed normal to the plane of the loop away from the reader. Means the paper is receiving the magnetic field. Right? If I give you a north pole and south pole, which pole has the tendency to emit the field lines? It is the north pole, and the south pole has the tendency to receive the magnetic field lines. I hope this concept is clear, right, for everyone. So the paper, like how you are supposed to visualize it, the paper on which you are writing is the south pole. Then you are the one who is seeing it, right? So you will act like north pole. You're able to understand? So the paper is the south pole and you're going to act like north pole. Under what scenario? If there is an into mark on the paper for magnetic field. Am I clear with this? Second. We know that flux is equal to, what is the basic formula for flux? It is BA cos theta. So flux is equal to BA cos theta. Then flux is dependent on the magnetic. It is dependent on the area of cross section. It is dependent on the orientation of the coil with respect to magnetic field. So flux is a function of how many parameters? 3. What are they? Magnetic field, area, and orientation. I hope this point is very simple. So generally, when you see a problem, right, we know that flux has to change with respect to time. Right? It is then EMF will get induced. Here, what will happen is, generally, if you see, out of the 3 parameters, one parameter will be changing and the other 2 will be constant. Not like all of them will change with respect to time. No, that will not happen. Sometimes magnetic field will change, sometimes area will change, sometimes orientation will change. So in this context, what I'm trying to say is, in the first one, there is a rectangular loop. So rectangular loop has an area associated with it, right? Now, as this rectangular loop is entering into the magnetic field, what is changing with respect to time?
Flux is changing.
No, not flux. In the flux is changing due to which parameter? Is it because of magnetic field, area, or orientation? When this coil is entering into the magnetic field, out of the magnetic field, area, and orientation, which parameter is changing?
Area, sir.
It is area. Very good. So it is area that is increasing. Now, second thing is, when area is changing and it is increasing, so can I say that the flux is increasing?
Yes.
So when the flux is increasing, right? When the flux is increasing, what kind of a polarity will get generated? Check your notes center. When flux is increasing, it is the same polarity as U that is going to get generated, because ABCD is a coil which is facing your north pole. So it is going to generate north pole. When it is north pole, current should be in which direction? It should be in the anti-clockwise direction. Right? When it is anti-clockwise direction, what is the direction of induced current? It is ABCDA. Okay. It is only because flux is increasing, same polarity as you are. Okay. If flux is decreasing, opposite polarity of you. Now, keeping the same context in mind, try the second problem.
So I have a doubt, sir.
Tell me.
How did we know it's anti-clockwise, sir?
I drew anti-clockwise only, no?
How is it anti-clockwise, sir?
Because north pole, no? Your north pole, the coil is facing you. So the current should get induced in such a way that there is a north pole getting generated, the side which is facing you.
Okay, sir, I understood.
And then it is anti-clockwise current, yes. In a similar way, when you take this second condition, It is a triangle, and the triangle is moving out of the magnetic field. So what is going to happen to the flux? The flux is going to will decrease. Correct? So flux is going to decrease. When flux is decreasing, what will happen?
Opposite polarity.
So it will be opposite polarity. So your north pole and the coil is facing you. So there should be a current in such a way that there is a south pole getting generated. For south pole, the current should flow in the clockwise direction. So what will be the direction of induced current? It will be ACBA. Important point to be noted here is with whatever point you are starting, you should end with the same point. If you're starting with A, you need to end with A.
Sir? Sir?
Tell me.
Sir, but this triangle is not moving in neither of the direction, no, sir.
They have given arrow mark.
Yes, sir, but it is not moving in north or south pole, no, sir. It is moving in another direction.
To understand the concept. Then you didn't understand the concept at all. What did I say? When it is moving out of the magnetic field, you check the direction. Is it
Yes, sir.
moving in? It is moving out of the magnetic field, right?
Yes,
When
sir.
it is moving out of the magnetic field, there will be one instant to be like this. So what is happening to the flux?
Decrease, sir.
Decrease means what polarity should get generated?
Okay, sir. Understood, sir.
Opposite polarity of U. Okay. In the same context, look at this one. Answer this. You guys think an answer? Steps to be answered. That's it. You need to look at the direction in which the coil
Flux
is.
decreases.
So the flux decreases.
That's right. So it should be
south pole will get formed.
very good. It should be opposite polarity as you are. Opposite polarity of what you are. So it is south pole. So south pole means clockwise current should flow. So clockwise means A, B,
A, B,
C,
C, A.
A, B, C, D, A. Yes. See, sometimes if you look at the answer, they would have started with B. See, for example, they have given the answer with C. So if you start with C, C, D, A, B, C, this is how you need to write. So with whichever point you're starting, you should end it with the same point. It is then it will be called as a loop. Okay. Am I clear, guys?
Yes, sir.
Okay, next one is slightly tricky, so concentrate and read the question properly. So there is a closed loop, okay, that is held stationary in a magnetic field. Let's say there is a magnetic field existing, and there is a closed loop which is held stationary in a magnetic field between north and south pole of two permanent magnets. They are also held fixed. So there is north pole, there is south pole. So they are also held fixed. Can we hope to generate current in the loop by using very strong magnets? So two important things to be understood here. The coil is fixed. Magnetic poles are fixed. Now the question is, but they told one thing. Is it possible for you to generate current if the loop in the loop by using very strong magnetic fields? Means if you use a very, very strong magnet and you create this kind of a scenario, is it possible for you to generate current?
No,
What is the answer? Answer is no. What is the reason?
There's no
Because
relative.
there is no relative motion. So no, the answer you are supposed to write is, you should not speak about relative motion, you should speak about flux. Since there is no
There's no
change
change
of
in flux.
yes, you should say since there is no change of flux because of the fixed positions of the coil and the magnet, there is going to be no EMF. How much ever strong magnet you want, you can use. but nothing is going to happen. First, so what did Faraday say? It is there should be a change of flux. As long as there is a change in flux taking place, for that complete duration of change of flux, there will be an EMF. The minute the change of flux stops, EMF will stop getting generated. Okay. So have this point in your mind. B. So there is a closed loop which moves normal to the constant electric field between the plates of a large capacitor. Is the current induced in the loop when it is wholly inside the region between the capacitor plates, when it is partially outside the plates of a capacitor? So let me draw this diagram and show. So tell me, you have large capacitor. We know that the field between the capacitors is a constant, right? Electric field is sigma by epsilon naught. I hope you guys remember this. Is a current induced in the loop when the closed loop is wholly inside the region between the plates of the capacitor. When it is like this, is there going to be an EMF induced? Is there going to be an EMF induced? Secondly, when it is partially outside the plates of the capacitor and the electric field is normal to the plane of the loop. So what do you think will happen?
So can you explain this question again, sir?
Read it again. There is a closed loop which moves normal to a constant electric field between the plates of a larger capacitor. So in this case, the loop is inside the capacitor, between the plates of the capacitor, and it is moving. Okay, first point. Now, if it is moving, is there a possibility of EMF getting induced in this? So we will concentrate on the first case now. What do you think is the answer? What do you think is the answer? The answer is again no. And the reason is very simple. Because the electric flux is not changing. Okay. But this question, I would say it is tricky because you need to know some basics about electromagnetism also. There is something called as, I hope that they don't ask this question in the first term because since you don't have electromagnetic waves. Okay. But I will just give you an outline of a word. I cannot explain what it is now. There is something called as displacement current. Okay. Just have this word in your mind. That's it. So there is something called as displacement current that will get generated when there is a change in the value of electric flux within the coil, within the plates of the capacitor. Okay. Just have this word displacement current. Don't think too much about it. If there is a concept of displacement current, then yes, you can think of EMF getting induced in this case. So if at all this question comes, you can just have the answer in your mind and write. Okay. What is the answer? The answer is no, because current cannot be induced by changing the electric flux. It's very simple. That's it. Okay. So what should change for current to get induced? There should only be a concept of change of what flux?
Magnetic.
Magnetic flux. So that is very important. So they can confuse you by using the word electric flux also. No. Okay. So I hope this point is clear, right? I want you to mark it as important and just have the answer in your mind. So what is the answer for this problem? You cannot generate current or you cannot induce current by changing the electric flux. Rather, you can only do it by changing the magnetic flux. That's it. Okay. C. Try the part C. No? I want you guys to try it. 1 minute. I'll show you the question. So there is a rectangular loop and a circular loop, which are moving out of a uniform magnetic field. So here, thing that you need to understand. So always, whenever there is a question from electromagnetic induction, the first rough work you're supposed to do is write down this formula. Okay. So once there's a technique I follow. So write down this formula and check if the magnetic flux is changing or not. If it is not changing, then you can directly write the answer as no. If it is changing, then you need to think of the parameter due to which the flux is changing. Okay, here, look at the way I'm reading the question. There is a rectangular and a circular loop. Both are closed surfaces. That's what I understand. Are moving out of a, so whenever there is a loop, even before I see the diagram, I can tell that whenever a loop is moving out of a magnetic field, is the flux going to decrease or increase? Sorry?
Decrease, sir.
Decrease. Even before we draw the diagram, we can know. Moving out of what? Of a uniform magnetic field. So B is constant. Okay, of a uniform magnetic field region to a field-free region with a constant velocity V. Okay. So whenever this concept of a coil moving out of a magnetic field comes, then what parameter changes?
Area changes.
This is the area that is going to change, and orientation is also constant. Okay, but here the question is slightly tricky. Observe. In which loop do you expect the induced EMF to be constant during the passage out of the field region? The field is normal to the loops. So they didn't ask you the direction. Rather, what are they asking you? In which loop do you expect the induced EMF to be constant? Now let us look at the diagram. Right. Now, I know that EMF is equal to delta phi divided by delta t in terms of magnitude. So let's first try to understand the question. What do they mean by the induced EMF being a constant?
It will
Means,
not change in this.
yes, it should not change with respect to what? With respect to magnet, with respect to time, because EMF is dependent on time, right? So if EMF has to be constant, guys, understand this. If EMF has to be constant, can I say that the rate at which the flux is changing for a given time should be a constant? Means if when the loop is coming out, if there is a change in flux of x unit in 1 second, okay, let's say the loop is taking 5 seconds to come out, guys. Okay, so in the first second, let's say x units of flux has changed. For EMF to be constant between the first and the second, that is the next 1 second, how much should be the value of change of flux? For EMF to be constant, is it not supposed to be the same x? So between 2 seconds to 3 seconds, it should be the same x. So what I'm trying to say is, for every particular second that you're taking, the change in flux should be a constant for the EMF to remain a constant. Now, keeping all this logic in mind, tell me whether it is going to happen for a rectangular loop or the circular loop, keeping in mind that the area is the parameter which is changing the flux. Did you guys understand till what I explained? So what I'm trying to say is, let's say in the first second, the loop is like this. Okay. Then this is the area that has come out. In the next second, what would have happened? This would be the area that has come out. Since both the loops are moving with constant velocity, can I say that this distance and this distance will be the same. If it is L, this is also going to be L. And this height is obviously X. So can I say that the area of the portion that is coming out in the case of a rectangle is going to be constant always? Whereas with respect to a circle, what will happen? If in the
Area
first
coming out will be different.
if the first cycle, if the area that has come out is this much, and in the second condition, it will be this much. Are these two areas going to be the same? Because of
No,
the
sir.
curvature that the circle has, the area that is coming out at every instant is going to change. So that is what the question means. So the reason that we need to write is the induced EMF is expected to be a constant only in the case of rectangular loop. In this case, the case of circular loop, the rate of change of area of the loop during its passage out of the field region is not a constant. Hence, induced EMF will be varying accordingly. Clear, guys? There's also an important point. These kind of questions come. This can be asked as an assertion reason question. For that matter, anything can be asked out of the three. Okay. Next, the last one is predict the polarity of the capacitor in the situation described by figure 6.9. So if you observe, there are two magnets. There are two permanent magnets where the left side magnet has the north pole closer to the coil with the capacitor, and the right side magnet has the south pole closer to the coil with the capacitor. I hope that point is clear. Right. Now the question is, see, whenever you have these kind of loops, right, one point I would like to mention is you might have a confusion of how you are supposed to see the loop. So if I draw a loop like this, then I can see from any of the directions. For that only what they will do is in the problems, they'll give you axis like this. Okay. So the axis where you are able to see the center, the axis which is reaching the center is the side from which you are supposed to see. That is the side you are actually able to see. Okay. Is that clear? So the side, whenever you see the axis, which is entering the center, is the side from where you are supposed to see. Now you tell me, guys, when you're seeing from this side, you have the south pole moving towards the coil. When you have the south pole moving towards the coil, what pole will get generated?
South pole will get generated.
That will be a south pole. So due to south pole, what will be the direction of current? It will be clockwise. So when it is clockwise, then we can say that B should be positively charged and A should be negatively charged. But there is a mistake in the answer that they have given. This is wrong. Okay. So for the plate B should be positively charged and the plate A should be negatively charged. Okay. And see, I would like to stress on one more important point. When you see from the side that I've drawn the eye, the current is in the clockwise direction. Whereas when you see from this side, it will be in the anti-clockwise direction. Check whether that is happening.
Yes, sir.
When the north pole is moving towards the coil, the back side will be north pole. North pole means anti-clockwise. You're able to understand? For example, had the question been given like this, let's say this is not given. Okay, had they given it like this, then what will you say?
South pole will be generated.
Not a possible condition. Why? It is not a possible condition because both the sides will have south pole. Right? When both the sides are south pole, who will decide the direction of current? Means when you see from both the sides, current should flow in the clockwise direction, which is obviously not possible. Okay. So these are all the important points that you need to concentrate, guys. So whenever you're solving a problem, don't just blindly solve it. Try to understand and then proceed. As I told you, this is the only tricky part. The other questions are very easy. Okay. So we'll do some exercise problems. First, we'll start with 6.2, then we'll go to 6.1. Tell me how to do this. You guys do it fast. Using Lenz law, use Lenz law to determine the direction of induced current in the situation described by figure 6.19. A wire of irregular shape turning into a circular loop. In the first case, which pole are you guys?
You can consider as well any poles, or should it always be north?
Guys, am I audible? Sorry, I had a power cut. Wi-Fi got disconnected. Am I audible?
Yes, sir.
Yes, sir. Yes.
Okay, what were we discussing? 1 minute.
A part of 6.2.
Yeah, A part of 6.2. Right. Yeah. So the paper is acting. What happened? So the paper is acting like south pole. Correct? Paper is acting like south pole. So obviously you are going to be the north pole. Right. Now look at this. So whenever you have these kind of diagrams, it is understood that the magnetic field is uniform. Because they're equally spaced. Magnetic field is uniform. Then what is happening to the area?
It's increasing, sir.
So area is increasing. So what pole will get generated? So area increases, flux also increases. Flux increases.
Polarity will get generated.
So it is going to be the same polarity. So when it is the same polarity, what will be the direction of current? Is it same polarity as whom? Guys, I don't have energy to ask multiple times. Same polarity as whom?
Yes, sir.
You are acting like
North pole, sir.
North
North pole.
pole.
So current should be in the anti-clockwise direction.
Anti-clockwise direction.
That's right. Anti-clockwise. Now, what should be the direction? Can you tell me? AD,
ADCBA.
ADCPA. That's right.
So I have a doubt here, sir.
Please tell me.
How did we find that paper has south pole, sir?
Paper has because see, it is receiving into markments. Into markments, it is going into the plane of the paper. So who's receiving the magnetic field? Paper is receiving the magnetic field, and you're the one who's emitting the magnetic field.
Okay, sir, I understood.
Understood? Yeah. In a similar way, look at this context. Then the paper will act like
North pole.
North pole.
North pole, and you will be acting like South pole. So you should be concerned about yourself. Now look at this. Is the area decreasing or increasing?
Decreasing, sir.
So area decreasing, flux will decrease, as a result of which polarity
Opposite
will
polarity.
be opposite as you are. So what is the polarity you have? South pole, no?
South, sir.
So it should be north. Answer will be A dash, D dash, C dash, B dash, A dash. Clear?
Yes, sir. Clear, sir.
Yes, sir.
Right. So try the 6.3. Solenoid with 15 turns per centimeter. So small n is equal to 15. Has a small loop of area 2 centimeters square. Placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 seconds, what is the induced EMF in the loop while the current is changing?
We have to use the average formula, right, sir?
Yes, because 2 ampere to 4 ampere in 0.1 seconds. So it is a measurable amount of time. In itself is like between only. In 0.1 seconds. So how to solve? EMF is equal to N into delta phi divided by delta T. Or you can write delta phi by delta T in terms of magnitude. So what is delta phi? So here if you observe, the magnetic field is what, guys? Mu naught into small n into I. Area is 2 centimeters square. So what will be the value of flux? So E will be equal to magnitude of mu naught n into I 2 into A minus mu naught into n into I1 into A, the whole divided by delta T. Did you guys understand why I wrote mu naught Ni2 minus mu naught Ni1? Here area is constant. It is because of the current, the magnetic field is changing. It is because of the magnetic field, flux is changing. Clear, guys? What is the answer? Do it fast and tell me. Okay, that part I'm leaving it to you. You can do it later. Next. Wait, let me erase all these things. Try these problems. Predict the direction of induced current in the following situations. First one. South pole is moving towards the coil. So what pole will get generated?
South pole will get generated.
South pole.
So south pole means current will be in the
Clockwise direction.
clockwise direction. So clockwise means observe. When I zoom it, I'm able to observe that when the current is in the clockwise direction, first the current will go in this way. And they will enter the loop here. Right, when that is the case, what will be the direction of induced EMF? Induced current. Q R P Q. Okay, using the same logic, you guys solve this problem and tell me. So if you have your eye here, south pole is moving closer, so this will act like south pole. What will be the direction of current? Clockwise. So when it is clockwise, the current will first go here. Again, it keeps on going, and the last loop, the current will come out like this, and it will go in this manner. So answer will be PRQP. And what about this thing?
There also south pole, sir.
So here it will be south pole. So obviously the other side has to be north pole. So north means anti-clockwise direction of current. So anti-clockwise direction means the current will first come like this, then it will go in this way. Okay, answer will be YZXY. Did you guys understand what logic I used? I'm only concerned about the side that I'm able to see. I always think like that. I will always start with the side which I'm able to see. So south, obviously, if this side there is south pole getting generated, exactly on the other side there will be a north pole that will get generated. Okay, one last problem, then we can wind up. So if you close this key, what will happen? So when you close the key, flux is increasing because current is going to pass. When the key is open, current is not there. Current is zero, flux is zero. But when you close the key, current will produce magnetic field and the flux will increase. So when the flux has got increased, what will happen?
Polarity will be the same.
So this side, the polarity will be the same. But observe, I told you, how are you supposed to see? You are supposed to see from the side where these dotted lines come till the center. Okay. So since this side flux is increasing, and you see from this side, what is the direction of current?
It's clockwise. So
Clockwise. Very good. Then it is going to act like north pole. Then the
It's
inner
south
face
pole,
is
right,
north
sir?
pole, and this side will be south pole. So when it is south pole, current will be in the clockwise direction. So answer is XZYX. Is the answer. Okay. XZYX is the direction of current in Am I clear, guys?
Yes, sir.
Yes, sir.
So these are all some problems. The remaining three problems you can try it and let me know if there is any doubt in tomorrow's class. In the next class, I'll start another topic called as motional EMF. So that will be the topic for tomorrow's class. Okay. So, is there any other doubt from today's class?
No, sir.
Okay. I can buy it.
Thank you, sir.
Thank you, sir.
Thank